so you can always ask me if I do. But here we go. We're talking about limits. I'm actually doing 2.2 first, but my homework that's on WebAssign is listed in the order that I teach, okay? So you don't have to care too much. After I do section 2.2, I go back and do 2.1, okay? So we're talking about limits, and I guess the first question should be, what is a limit, right? So I've got an informal definition here. I like to say, and this is my definition, and again, my job is to interpret the book for you. I'm going to take the super nerdy book and say it in a way that you're going to understand it. But you're going to read the book and make sure you make that connection, okay? And then you got to develop your own way to interpret the book, right? So, but I like to say the limit is a predictable height of a function. So we were talking about that limit with the secant line, the slope of the secant line, right? We were talking about that one limit, right? With the slope of the secant line. So we had one secant line and then another secant line and then another secant line. And then from there we could predict the slope of the tangent line, right? And again, this is section 1, 2.1. This concept, secant tangent problem, right? So, but I can see that the slopes of the secant line are becoming the slope of the tangent line. And so I'm going to make a prediction about it. And the function piece is our derivative when we get there, when we learn that. But it's pretty easy to think of this as the limit is a predictable height of a function, right? It's pretty simple to think about that. Like the limit of, as x goes to 2 of x squared, it's pretty easy to think of that, isn't it? Without me doing much work at all, I could think about what's going to happen if I put 2 in, right? Do you hear that as a prediction? What would happen if I put 2 in? Well, it's going to be 4, exactly. So we're going to look at different types of limits: graphical, algebraic, and numerical. I think this is homework 1. This is homework 2. This is homework 3. The algebra ones are the ones I'm most interested in. Anyone can open a graph and see where the height is, right? How do you show me that you have understanding of that on a test? It's not easy. So most of the things we'll be doing will be things that you have to use algebra to manipulate to find an answer, right? So, but you've got these other processes that will help you verify. You could look at the graph. Does it go to a height of 4 there? You could do a table, and I'll show you how to do all of this, okay? So, and you can see it's very easy, isn't it? Calculus is very, very simple and very intuitive. But verifying things is not. That's when the Algebra 3 hell comes in, okay? So, graphical limits are very simple. I want to talk. So by the way, how did I get this limit? How did I know that it was going to be 4? I mean, yes, I could look at the graph, but what did I really do? Just plug the 2 in, right? And so that's going to be one of our first things we always try is if you could just plug in the value, right? If you can plug in the value. Like if I asked you the limit as x goes to 0 of sine of x over x, right? When I try and plug this value in, what do I get? I get sine of 0 over 0, right? So definitely a problem, but what is sine of 0? Just yell it out for me. 0. So I get 0 over 0. Can I calculate a 0 over 0? No. Well, not yet. After this course, yes. After this course, you'll really understand what it means to divide by 0. And then 0 over 0 is even more trouble than just plain over something over 0, right? In fact, you already know that 5 over 0 is what? Undefined is what I like. Undefined means it's either positive or negative infinity, but I don't know which one it is. It's either positive or negative infinity, but I can't tell which one. Right? If I took $5 and 5 divided by 0 is bigger than 1, right? If you think about it, 20 over 5, 20 over 4, 20 over 2, 20 over 1, what's happening to these answers? They're getting larger, so when I divide by 0, it's still getting larger, right? So it's telling me that it's going to positive infinity. So it's a tricky thing, but you'll understand this one. This one we like to call the indeterminate form. Because sometimes it's 1, sometimes it's e, sometimes it's infinity, sometimes it's 7, sometimes it's -3. I can't tell what it's going to be, and it depends on the function that I'm starting with, the numerator I'm starting with, and the denominator I'm starting with. It turns out that this limit is easy to find graphically. It's 1. So I could look at that function, limit as x goes to infinity. The sine of x over x is 1. And in fact, I'll invite you to, anytime you can, take a look at things graphically. What did I do? Don't tell me. Where the heck is my keyboard? Oh, there it is. So f of x or y equals is fine. Y equals, oops, I don't like the capital. I don't think it would make a difference, but y equals sine x, oops, come on, Robert. I don't have a keyboard, that's why I'm sine x over x. So I can clearly see, right, the height is 1. And I got my graph wrong. It should be dampening to 0. This is a dampening curve, right? Sine is at most what? 1 and at least -1. So I'm going to at highest go up to 1 or down to -1, but I'm dividing by x. So when x gets bigger and bigger, it crushes the numerator, right? So look at the graph all the time when you do something. It'll certainly tell you quickly if you got it wrong, right? So graphical limits are pretty darn easy, right? Numerical limits are easy as well. Let's do a numeric limit together. So this is a table method, or however the book says it. So let's say f of x is 2x minus 1, and we want the limit as x goes to 0 of 2x minus 1. Now this one I can just plug in, right? This one I can just plug in. And like I said, when you can just plug in, plug in. So what's my limit here? -1, yeah. But I want to see what it's like to do this on a table as well. So I have to approach from the left and from the right. If I look at this graph, right? Let's see, 2x minus 1, right? When x is 0, I get a -1. When x is 1, I get a 1, right? So it's pretty clear that if I'm walking down this hill, right, from the right, when I finally get here, I'm going to be at a height of -1, right? That's obvious, right? Right, because so my x values are moving left and right. So that's me. I'm walking down the hill, but I'm moving right to left, right? And I end up at a height of -1. And same thing if I'm walking up this hill, right? Again, when x is 0, when I get to that y axis, I'm at a height of -1. So I have to think of things left and right. When it's graphical, it's obvious. We're so used to looking at a graph, we look at the point, we are kind of approaching this from the left and the right. But they have to match up. So I need an x and an f of x from the left, and an x and an f of x from the right. And so when I'm approaching 0, I want to get closer to 0 from the left. It has to be negative, right? So we're talking about negative 0.1, negative 0.01, negative 0.001. By the time you get to gas station money, it should be obvious. You know what I mean by gas station money? If you go buy gas, it charges you not by the penny, but by the tenth of a penny. Right? There's 3 decimal places to make it look like the gas price is cheaper. Right? So by the time you get to that third decimal, it should be obvious, right? And so what do I get here for numbers? What do I get? I got low battery. 2 times negative 0.1 minus 1, right? Negative 1.2, yes? And when I put the next one in, what do I get? 2 times negative 0.01 minus 1, I get negative 1.02. And now I don't even need the calculator anymore, right? You can see what's happening very quickly. Where is it going? Nope. This is going to 0. That's what I want. I want x to go to 0. So where's the function going? -1. So you're just using the table to verify. Am I going to ask you to do a numerical method? No, it's too easy. It's too easy. I don't ask easy questions. Well, I do. The first question on every test or quiz is up at the top right corner. It says name blank, right? And don't copy on that one. So, but it's too easy. But this is a nice way for you to verify that you have a limit correctly. And so we say that the limit as x goes to 0 from the left of f of x is -1. Look at that notation. It's a little bit weird. It's like a exponent, but it's just a negative symbol. It means from the left. From the right, I'm going to put in positive, right? I'm trying to get as close to 0 as I can, right? And then see if I can make a prediction. And these are pretty obvious, right? Is it? I better double check it. 2 times 0.1 minus 1. No, it's not the same, sorry. Oops, that's still right. But this one is starts at 0.8, right? 2 times 0.01 minus 1. Negative 0.98. Negative 0.998. Someone verify for me there. Yeah. So you can see those nines are starting to take over, right? Yes, you with me? Now I can do the tables in the table feature here, but since I'm never going to ask you to do one of these on the test or a quiz, there's no real point for me to teach you how to do it on the table. Okay? Actually, maybe I should anyway. So let me do it. Well, I'll do a more complicated one on the table, okay? But so we've seen a graphical limit, we've seen a numerical limit. The ones that are really going to come into play are the algebraic limits. But before I do that, I want to talk about the formal definition. Are we okay? How is our speed here? You following everything? I'm usually not going any faster than this ever. And if I am, just tell. If I'm going too fast, tell me. And I have my remind open, so you can tell me if you don't want to say it out loud. You can send it to me in the remind, right? That's what that's there for. Okay. So numerical limit, graphical limit. I want to talk about the formal definition of a limit, and don't let this scare you, okay? So we'll say the limit as x goes to c of f of x is L if and only if, meaning equivalent, logically equivalent, if and only if. One implies this one implies what I'm going to write, and what I'm going to write implies this one. They mean the same thing. How's that? For every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus c is less than delta, implies the absolute value of f of x minus the limit is less than epsilon. I'll say it again. I told you, don't get scared. For every epsilon greater than 0, every positive number, no matter how small I make it, there exists another positive number, no matter that I have to find. There exists. This one says everyone. This one says I can find such a number, such that if 0 is less than the absolute value of x minus c, if my x's are getting closer and closer to c within this range of delta, remember how I did 0.1, 0.01, 0.001, right? Always keeping it bigger than 0 and making sure it's less than delta. Then my function should get really, really close to L within my bound of epsilon. What the hell does it mean? I'll explain it to you. But this is my formal definition. Remember how the limit was easy to find? Right? Remember how that part when I said plug in 2? And now you're going, what the heck is going on? This is the part of the calculus that is difficult. But finding the answer is intuitive and simple. Again, I'll say it again. The limit is x goes to c of f of x is L. If and only if, equivalent to this statement. For every epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than the absolute value of x minus c is less than delta, implies the absolute value of the function minus the limit is less than epsilon. So, anybody want any of those words written down there? Yes. For every, no matter what number I pick that's positive. Epsilon greater than 0. There exists, I can find such a number. I'll be able to find this delta. I'll be able to, I don't know if you'll be able to, but this is not on the test, okay? This is something I need to prove things to you. This class is not about proofs. This class is about finding limits right now, right? Which so far you see is easy. But for me to really get you to understand it, I need this kind of, it's a theorem, okay? Proved. Delta greater than 0, right? And I think the rest is fine, right? Oh, such that might need it, right? Such that. As mathematicians, we're really computer scientists. Look at all of the memory I need to say this in words. For every epsilon greater than 0, there exists a delta greater than 0 such that. I'm wasting memory. I'm wasting speed. I'm a computer science person. I want to say as much as I can in the least number of characters. Okay. Now, everyone okay? I just got a message from a student. I'm not sure if I'm in your class or not. What the hell? Good luck, buddy. All right, let's see if we could verify one of these, all right? And then I'll try and explain to you what it really means, or I'll try and give you my understanding of it, okay? So let's take a look at a simple problem like the limit as x goes to 0 of 2x minus 1 is equal to negative 1, right? We did this one already? Yes? If and only if, for every epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than the absolute value of what? X minus 0. Right, do you see that, x minus 0? I'm filling in that value of c. Implies the absolute value of 2x minus 1 minus the negative 1, right? I'm going to do f of x minus L is less than epsilon, right? I could simplify that, so let me simplify that, but don't let me lose you here. Just notice what I'm doing. I'm taking my formal definition. Right? Taking my formal definition and putting in the values that I can. So I see that c is 0. So I put that 0 in. Right? I see that my limit L is negative 1. So I put that negative 1 in. Right? Everybody with me? I see the function is 2x minus 1. So I put that f of x in. Right? And I could simplify this. So let me do that. For every epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than absolute value of x is less than delta. Implies, anybody figured that one out yet? What happens to the negative 1s? They cancel, right? So I just get a 2x in absolute value is less than epsilon. So it turns out that I could almost pick anything I want for delta here, but because the way I'm going to relate it to you as a target and a bullseye, right? Can you picture the archer shooting the arrow at that big white target in the distance, and it's got the red bullseye? Does anybody not get the picture there? Does everybody understand that? You can visualize that? I'm shooting an arrow, right, at that big white target in the distance, and there's a red bullseye in the middle. Or I'm playing darts, right? In a bar, that's more me, but not everybody understands that one. So it turns out I'm just going to let epsilon greater than 0 and pick delta equal to epsilon over 2. If 0 is less than the absolute value of x, which is less than delta, then we must show. What time is our class is over at what? 11:15, right? Yeah. That the absolute value of 2x is less than epsilon. Everybody with me? It says for every epsilon greater than 0. So I said, okay, let's pick a number bigger than 0. Fine, whatever it is. 5.3. I got to find the delta. There exists a delta. I have to find it. I know how to do it. That's how I picked up delta is epsilon over 2. In this particular case, almost any delta will work. Because I want to see the target, which is my epsilon, and my bullseye, which is my delta. I want to pick a delta that's smaller than the target. That makes more sense. I want to pick a bullseye that's smaller than the whole target. Right? If this is true, and so I assume it, then the next thing must be true. That's what I have to prove. If I'm 10 feet tall, I could dunk a basketball. If I'm a donkey with a friend named Shrek, I can speak. I have to assume the first part in order to prove the next part, right? So, absolute value of 2x, anything happen with that you can think of? The 2 can come out of the absolute value, it's already positive, right? And the 2 is still the 2, but what do I know about absolute value of x? What is it less than? What is absolute value of x less than? No. No. It's on the page. It's on the line above. Delta. So this is less than 2 delta, which is equal to 2 times epsilon over 2. And the 2's cancel, so I get my epsilon. The tricky part there is that once I start to manipulate this piece, I want to try and figure out how I can work in my knowledge of delta in here. So I got the absolute value of 2x. 2 is positive comes out of the absolute value. But I already know that the absolute value of x is less than delta. So now this part is less than delta, and the 2 is still the 2. Right? But I picked the delta, didn't I? Let's put that delta in. 2 times the delta, epsilon over 2. The 2's cancel, and I get my epsilon. So look at it. Epsilon is greater than absolute value of 2x. That's what I have to prove. When these are linear, they're very easy. Let me translate the formal definition. Is it okay? Can I move on here? I'll do another one. There's my center of my circle. And this guy's got a radius of epsilon. So, for every dartboard, for every target, there exists a bullseye. For every target, there exists a bullseye. And notice that the target, the whole big white target, has got a radius of epsilon. I'm stressing that that is a radius in the y direction. What in the formal definition is telling you that? What is telling you that epsilons belong to y's and not x's? What is telling you in the definition that the epsilons should be related to y values? Exactly. The epsilon is related to the function f of x. That's a y value. There's a bullseye. There's a bullseye. There's a circle with a delta radius in the x direction. What's telling you that delta is related to the x values? Look at my highlighted in blue. What's telling you that the delta is related to x values? It's dealing with that x minus c, both x values, right? Such that if I restrict my x values within delta, so I'm saying I'm going to shoot an arrow at my target, but I'm going to put up like you know when you go bowling when you're a little kid, they put the gutter guards up. I'm going to put gutter guards up for my arrow so it won't go left or right of the bullseye. So narrow down where my arrow can go with, like, I don't know, plywood or whatever. So it's stuck within the width of the bullseye. So I'll never hit out here. I will never hit my arrow out here. This will never happen. I could hit here, okay? But it will never hit out of that range of delta, right? I'll never hit outside this range of delta. And what is the absolute value giving me? What's the purpose of the absolute value? Left and right side. I could hit right of the bullseye inside or left of the bullseye inside. Left of the absolute center, right? But still within the range of the radius of the bullseye. What else does this thing say? What else? What's this part mean? So what does that mean about my x value? It will never be exactly c. Remember what I did with my numerical? I put in 0.1, 0.01, 0.001. I never actually got to the c value. I want to get as close as I can and then make a prediction. Right? Like I want to walk halfway to the wall. Okay, I'm going to walk halfway to the wall. And then I'll walk halfway to the wall again. And halfway to the wall again. Will I ever get to the wall? Oh yeah, this is calculus. I've got an infinite number of things to do, and impossible to do them all. But my instincts, mathematical instincts, are so good I can tell that I can get the wall. So with it, Zeno's paradox. But so I'm gonna never allow my arrow to hit outside of that radius of the bullseye. And then what's going to happen is I'm going to get my limit. Okay. This first thing says what? This is first thing. Every target, every single target I make. So what am I going to do is I'm going to take my target and shrink it down to what? Almost nothing, right? Remember, epsilon's got to be bigger than 0, but I'm going to make it almost nothing. And so what happens when I make this thing almost nothing? Where does this arrow shot go to? If I go almost to nothing, where is that arrow now? Where? Yes, right on this center. It's the limit. Since I picked pieces between that radius of the bullseye, and I hit the board, when I make the whole board as small as I possibly can, I have to be at the bullseye. I have to have hit the limit. All right, here we go. Algebraic limits. This is the good stuff. This is the stuff. This is your first quiz, right? This is the first question on the test, on the midterm. So, and this is homework 1. Homework 2 is graphical. Homework 3 is numerical, okay? Now, I need something to do this, okay? I need something to do this. So we're going to look at our first function, f of x. And it'll be like a x squared minus 4 over x plus 2, okay? And so you know, what's the domain here? Yes, x can't be negative 2. If I plug in negative 2, I'm dividing by 0. Not that big of a deal. And this function can be simplified, right? Yes, you with me? So those x plus 2's really can cancel, right? But I can only say this is equal to x minus 2. This is still equal to the original function as long as I consider that domain. I'm not allowed to plug in negative 2 for it to be f of x. For it to be g of x, I can. F of x is x minus 2 as long as I don't use negative 2. G of x is x minus 2 always. You with me? The domain of G is what? All reals, right? What does f of x look like? What does g of x look like? This is f of x. This is g of x. What's the difference? What's the difference? What do you see? What's the big thing that you see? The hole. The hole, right? There's a hole in this stuff. The g of x, there's no hole in it. I can put anything I want in. It means all numbers. F of x is, it looks identical except for that one point is missing. Right? And I would ask you, put this in the calculator, put this in the calculator. You won't see, you can't see the hole in the calculator, but you'll see that they're the same function. And so, what I'm going to say is, I need a theorem for it, that the limit as x goes to negative 2 of f of x is the same as the limit as x goes to negative 2 of g of x. which is the limit, oh, -2, sorry. It's the limit as x goes to -2 of x minus 2, which is -4. And I have a function that if I plug into, I get 0 over 0. I've got to find a replacement function. And so you can tell on the graphs, the functions are the same except for at that one point. But remember, what's with my formal definition? What's with my formal definition? For every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x plus 2. That's x minus a -2, x minus c, right? Implies that f of x minus a -4, right, is less than epsilon. What number am I not allowed to plug into f of x? And why is this good then for me? Why is this good then? Because I can't, right? I can't let that get to 0. I can plug in -2.1, -2.01, -1.9, -1.99. I can get really close to -2, but this definition tells me I can't plug in -2. But I can still get to that limit of -4. And so now, what do I do to do this from this step to that step? What do I do? What do I do with this? What's the only thing that's bad here for me? That's okay, that's okay. That's great. No problem, no problem. Something else has to change. F of x becomes. Since the functions are exactly the same except at -2, but I can't use -2 anyway, I can change the function. And how do I change the functions? Algebraically. What did I do? What was my algebra I did? I factored. And so there's going to be 3 processes right now. More to come, but 3 right now. The first one is if I have polynomial over polynomial, factor. The second one is if I have fractions within fractions, I find an LCD. And the last one is if I have radicals, I use a conjugate. All right, let's do another, right? Yes, you with me? Let's find the limit as x goes to 1 of x cubed minus 1 over x minus 1. So if you're in my pre-calc class, I tortured you with this stuff so that when you got here, it would be easy. What happens when I plug in 1? 0 over 0, right? Indeterminate form. So I can't plug in 1. Oh, but I know if I'm doing a limit as x goes to 1, if I could just replace my function, I could get this. Right? I could get this limit. Right? I might want to do it numerically to verify. I might want to just graph it and see what height I hit. Right? But I know Robert's going to ask me to do the algebra. Right? So let's do some algebra. X cubed minus 1 over x minus 1. You should remember that that is x minus 1 times x squared plus x plus 1 over x minus 1. I don't remember that well. I usually do synthetic division. I'll check that 1 goes into 1x cubed, 0x squared, 0x minus 1. Do you remember doing synthetic division in pre-cal? I bring down that first guy, and then I multiply, and then I add, and then I multiply, and then I add, and then I multiply, and then I add. So I get a 0. And notice here that I got 1x squared plus 1x plus 1, right? That's this piece here. You could do long division, you could do synthetic division, you could have it memorized. A cubed plus or minus b cubed, right? Sum or difference of cubes, right? Remember that in algebra 2? I haven't had a mask on this long, ever. Not even Halloween. Right? It's hurt my ears right now, it sucks. And so, turns out that the limit as x goes to 1 of x cubed minus 1 over x minus 1 is the same as the limit as x goes to 1 of what? X squared plus x plus 1? And that's easy, I can just plug in. Notice once I plug in, the limit symbol's gone. Question? No? Anybody? 3. So the algebraic limits definitely, you can see, you can verify for me that you're understanding what's going on. Right? And then what would I ask you to do on your own? Look at your calculator and see if you hit 103 then. Do it numerically. Let me do this one numerically, okay? I guess it would be nice to look at this actual curve here. So what did I have, an x minus 1 downstairs? Yeah. Oops. And then upstairs I have x cubed, right? Where is my, sorry. Where's my caret? Do you see it there? Oh, go back to ABC? I go to my, where's my caret at? Oh, forget it. I'll just plug in my keyboard, damn it. Thanks, Ryan. X cubed minus 1, right? And I'm interested in what x is 1, right? So do you see that I hit a height of 3? Right? At x is 1, I hit a height of 3. That's my limit, right? Simple, right? Let's do it numerically. So when you do it numeric, when you're working on your test, you can use a TI-83 or an 84, right? And I know this is hard to see. It's as large as this thing gets on the screen. But I want to go into y equal, and I want to put in my function. So parenthesis, oops, sorry. Oh, parenthesis, x cubed minus 1, close parenthesis, divided by parenthesis x minus 1. Anybody doing this with me at the same time? Okay, so don't let me go too fast here. If you don't have this calculator, you can borrow one at the Learning Center, at the Math Science Learning Center in the first floor of the Math Pavilion. I'm on the second floor of my office. So you can borrow one for the semester. I want to go to second table set. Second table set. Yes, you with me? So I hit second function table set. And I want to change my independent to ask. I want to change my independent. So I scroll down to where it says auto, move over to ask and hit enter. Don't let me go too fast here. If you're lost, stop. Put the function in, right? Wrapped, numerator wrapped, divided by denominator wrapped. And with the second table set, we change the independent to as. Now I'm going to go to second table. So second table. So second table, this is going to give me a blank table. So second graph or second table, right? And now I can plug it. Remember, where do I want to get close to 1, right? I want to get close to 1 from the left and from the right. So let's do from the left first. So 0.9. 0.99. 0.999. 0.9999. It's enough to gas station money. I should be able to predict right at that point, right? Once I did 0.999, I could see my 2.9s, the 9s started to take over, right? So I know it's going to where. You probably didn't put your function in right. Double check that your function in has got wrapped numerator, x cubed minus 1 wrapped, right? Not in a Christmas present or a music sense, but wrapped in parentheses, divided by denominator wrapped in parentheses. And your table, after you change your function, your table should adjust. So I want to do numbers from the right of 1 now. So for example, what? It's a number to think of bigger than 1 because it's going to get close to 1. 1.1. So when I was at 0, I had a kind of symmetrical table. But when I'm at another number, I'm going to be 0.9s to the left and 0.1s to the right. So 1.1, right? 1.1, enter. 1.01, enter. 1.001. That should be enough. I should be able to predict 3 at that point. Easy, right? Numerical limits, easy. Graphical limits, easy. What are you going to have to do? You're going to have to do them algebraically, and then before you walk out, you'll check it numerically and know you got it right. Or check it graphically and know you got it right. I love to take a test because I would put a check mark on the page when I knew I got it right, and I wouldn't have to think about it again. Right? In fact, I didn't even have to look at the page when I got the test back. I knew I got it right. Let's do another algebraic limit. Okay? What time I got? Ooh, I got 15 minutes. Thank God. Huh? I might end a little early today, in just in case you want to talk to me about anything. Okay? And then most of the time I will be ending early. I would end at 10 at the latest. Sorry, 11. And then give you a quiz, right? And so if you did the quiz in 2 minutes, you leave. If you needed 20 minutes, you take it, right? Let's just make it. We'll do a quiz at 10. Whenever we do a quiz, we'll do a quiz at 10. Eleven, sorry. Thank you, Ryan. Let's do another algebraic limit, okay? We'll see if we do a couple more. We'll do we did 2 already we did one with linear, we did one with the polynomial, we did 2 with the polynomial, right? Polynomial, poly over poly, factor is my key. Let's do one with something called a rational expression, or a complex, sorry, let me just write it first. Give me a second, don't copy yet. F of x is x minus 2 over 1 minus x over 2. There we go. So I can see fractions within fractions. Whenever I see this, I'm going to first try and clear fractions. It'll turn into polynomials, right? So I want this limit as x goes to 2. So if I plug in 2 right away, I get 0 over 0, right? You see that, yes? So I got to manipulate this. When I have something called a complex fraction, which is a fraction within fractions, fractions within fractions, I want to do something called clear fractions by finding the interior LCD. So I want to find this interior LCD. I'm looking at all the interior denominators. I only have one. I don't want to look at the whole denominator, right? You with me? I only want to look at the denominators of inside fractions, right? So I'm going to manipulate this with a 2 over 2. I'm going to take that LCD over itself and multiply. So I'm always multiplying by 1, right? I'm multiplying by 1 doesn't change anything. This is still f of x. You with me? And so what do I get here? I get 2 times x minus 2 over 2 minus x. I should see opposite factors there. If you don't see opposite factors, factor out a negative. Right? I factored out a negative from either upstairs or downstairs, your choice. And now those cancel. Right? This is still f of x as long as I keep my domain. Or I could think of it as a new function and I don't care about the domain. So the limit as x goes to 2 of x minus 2 over 1 minus x over 2 is the limit as x goes to 2 of negative 2. Well, duh. What height am I at if I'm at a height of negative 2 all the time? What height am I at if I'm at a height of negative 2? If I'm at a height of if I'm 2 feet underground, where am I? 2 feet underground, right? Easy, yes? I can verify by looking at the graph. I can verify by doing numeric. Another? No? This is easy, right? Am I right or no? It's easy. You got to know what to do, and I think that's what happens in math. Is nothing we do is difficult, but remembering what we do is what to do is difficult. And that comes with practice. Is brushing your teeth easy? Hell no. It's very complicated. Very, very complicated, but we've done it so many times that you don't even have to think about it anymore. In fact, if you try to think about it, it's impossible. What do I do first to brush my teeth? What do you do? How do you do it? Pick up the toothbrush? So wet the toothbrush magically? I gotta turn the faucet on? Put the brush under the... It's very complicated, I'm telling you, it's very complicated. I got a wet brush now. Do I just pick up the toothpaste? I got to put the brush down, pick up the toothpaste onto the cap. It's very complicated. But we've done it so many times, it's easy. You don't even have to think about it. And that's the same with math. You got to practice. I'm really good at watching TV because I do it every day. That's a joke. So let's do another one with a fraction, okay? Yes, of course. Yes, because what is a constant? It's a height. And what is a limit? A height. Right? So when I'm asking you what's the height at -2, the answer is -2, right? And I could also think of this as, okay, I did my replacement function, right? There's my replacement function. And now what am I supposed to do? Now it's safe just to plug in, but there's no x's. I can't plug in. Right? I'm trying to make it safe for me just to plug in a number, right? Okay, we ready? Let's do the limit as x goes to 3 of 3 minus x over 1/3 minus 1 over x. I mean, I'm just making these up in my head real quick, so I got to make them simple. But I'll give you my old quizzes and my old midterms, and then you'll see how complicated I can get. Okay? But it's never a different process. I've got something with a fraction with fractions in it. I want to clear those fractions. I want to clear those interior fractions. What's my LCD? 3x. Yes, 3x. She said just said 3, right? Yeah, I don't hear too well. So it's great when my girlfriend and I get an argument because this year I can't hear it at all. I'm just lying in bed. I don't know what the hell to say. That makes her more mad too, though. But eventually I'll get her to say she loves me. She'll say, I love you. What? I love you, and just start screaming, I love you, and that's when I know I'm loved. But she's yelling at me that she loves me. Yeah. I'm looking for interior denominators. So if I get really silly on this, I could see this as 3 over 1 minus x over 1 and 1 over 3 minus 1 over x. And I want to highlight all of these denominators, interior denominators, I call them. That's my own language. I don't know. The book doesn't tell you to do this. And I'm just doing the product of all of those. So my LCD, it's actually just, it's fine just to think of it as a common denominator. So I get 1 times 3 times x. So there's my 3x. Yeah, and it's that way every time. So I'm going to take my function, wrapped, numerator and denominator, and do 3x over 3x. Right? Okay, there's nothing to clear upstairs. So I'm going to let it alone. I'm going to say 3x times 3 minus x. But downstairs, I'm going to distribute it. I get 3x over 3 minus 3x over x. How are we doing? What's the domain on this particular function, by the way? What number's bad for me? It's always obvious. Where I want the limit is where I can't plug in. Where I want to know what the height of the function is, I'm not going to be allowed to put that number in. When it's an interesting problem. Right? So this is still f of x because I still can't let x be 3. And what do I get downstairs? X minus 3, right? I get another odd. I didn't do that on purpose, but I get another factor of a negative. Still can't let x be 3, right? You agree with me? This is still f of x. Is everybody okay here? This is still f of x. I can't put in a 3. So I'm not quite there to my substitute function yet. I want my function g of x, where I can put a 3. So I can finally cancel here. Right? So my substitute function is negative 3x. So I'm looking at this limit as x goes to 3 of f of x. Is now the limit is x goes to 3, not 0, right? Of negative 3x. Okay, well that's just, I can plug into that. So I get negative 3x times 3. Notice once I plug in, I take the limit notation's gone. You see that? Once I'm plugging in, I'm not doing a limit anymore. I know what height I'm at. Right? Negative 9. All right, there's one more rule we have. We have polynomial over polynomial factor. Complex fraction, find your LCD. And the last one is a radical. What are we going to do? Who remembers from our pre-calc class? So I've got 4 of you here from the pre-calc class. You remember what we had to do when we had a radical? Conjugate. We're going to use a conjugate, right? So let's do one more and then get out of here. I said I was going to end early, but I lied. Let's say, let's look at the limit as x goes to 4 of the square root of x minus 2 over x minus 4. So if I plug in the 4, do you agree I get 0 over 0 again? Yep. So I know I'm going to try and find a replacement function for that. So I got my function f of x. I want to find my function g of x. So f of x is square root of x minus 2 over x minus 4. And I see where the radical is. I want that conjugate. So I need rad x plus 2 all over itself, right? Is everybody with me? Good. I'm not going to manipulate downstairs. I want to see what happens. I'm going to leave it alone downstairs. But upstairs, I know I get, you remember this? A plus b times a minus b is a squared minus b squared. So the middle terms go away. That's why we're using this conjugate, right? So I get square root of x squared minus 2 squared. Or better yet, x minus 4, right? Still f of x, I still can't put a 4 in, right? But if I cancel these x minus 4 factors, all of a sudden I get my new function 1 over square root of x plus 2. That's my function g of x. So the limit as x goes to 4 of f of x is the limit as x goes to 4 of 1 over rad x plus 2. And now I can plug in that 4, right? And notice once I plug in, the limit notation's gone. I get 1 over 2 plus 2, that's 1/4.